Every single second, the world generates hundreds of terabytes of new data, photos, videos, messages, transactions, research results, AI-generated content, you name it. And all of this information has to be stored somewhere. In this video, we'll explore three main ways data is stored and accessed: DAS, NAS, and SAN. Whether you're setting up a home server or curious how enterprise systems handle petabytes of data, by the end of this video you'll understand exactly how these storage systems connect, how they differ, and why they matter. Let's start with the simplest form of storage, DAS, or direct attached storage. In our setup, we have a power supply, a motherboard, and several direct attached storage devices connected to it. In most personal computers, the most common type of hard drive uses the SATA interface. On the motherboard, these are easy to spot. The L-shaped SATA data ports ensure the cable fits in only one direction, preventing connection errors. Here, we have two SATA storage devices. One is a hard disk drive, which stores data magnetically on spinning platters. The other is a solid-state drive, or SSD, which uses flash memory instead of moving parts. Because hard disks rely on mechanical movement, they're generally slower than SSDs. However, when it comes to storing large amounts of data, hard disks remain the more cost-effective option. SSDs, on the other hand, are ideal for data that needs to be accessed quickly, thanks to their low latency and high performance. Both of these are classic examples of direct attached storage, devices that are physically connected to a computer. The next type of direct attached storage we find are NVMe drives. Like SSDs, they use flash memory to store data, but instead of communicating through the slower SATA interface, NVMe drives connect directly to the CPU over the PCIe bus. Because of this high-speed connection, NVMe storage delivers extremely low access times and exceptionally high transfer rates. While a typical SATA hard disk might take up to 10 milliseconds to access data, an NVMe drive does it in just a few microseconds. That's thousands of times faster. And when it comes to transfer speed, the difference is just as dramatic. A hard disk usually peaks around 150 to 200 megabytes per second. A SATA SSD can reach about 500 to 600 megabytes per second. But an NVMe drive can achieve speeds of up to 7 gigabytes per second, or even more with the latest PCIe 5.0 models. That's why NVMe has become the standard for high-performance desktops, gaming PCs, and enterprise servers, where speed truly matters. Next, we have storage devices that connect via USB ports. Their speeds can vary widely, depending both on the type of USB port and the technology used in the drive itself. Next, we move on to dedicated network-attached storage devices, or NAS. Unlike DAS, these storage units are designed to be accessed over a network. A desktop, laptop, or even a smartphone can connect to a NAS through a router or a network switch, making your data available to multiple devices at once. NAS units for home or personal use can house up to 8 drives, giving you plenty of storage space. Many also support RAID configurations, which let you combine drives for redundancy or improved performance. We will discuss RAID configurations in a future video. For a home network, even a simple gigabit Ethernet connection can make NAS a practical solution for storing media, backups, or project files. Next, let's move into the world of enterprise data storage. Here, we have a rack-mounted blade server setup. Each blade contains a server-grade motherboard, a high-performance CPU, and DDR5 memory for maximum speed and efficiency. Unlike desktop computers, most enterprise servers don't store large amounts of data directly on local drives, except perhaps for an NVMe drive used as a cache to speed up operations. Instead, these servers rely on separate storage systems, typically NAS or SAN units, to hold and manage the bulk of the data. This separation allows enterprises to scale storage independently of compute, optimize performance, and implement advanced features like redundancy, high availability, and fast data access across multiple servers. Now let's focus on an enterprise-grade NAS unit mounted in a rack, packed with 20 SAS hard drives. While the drives store the data, the circuit board inside this NAS is where all the intelligence happens. At the core, we have a server-class CPU, often Intel Xeon or AMD EPYC, designed to handle heavy workloads and simultaneous requests from multiple servers or clients. Surrounding the CPU is high-speed ECC RAM. This memory acts as a cache, buffering read and write operations and ensuring data integrity, which is critical in enterprise environments. Next, there would be storage controller chips. These manage all 20 SAS drives, coordinating RAID operations, parity calculations, and data striping across the drives. They ensure that even if one or more drives fail, the system can continue running without data loss. Each of the drives in this unit will be connected via SAS, serial attached SCSI, interfaces. SAS provides high reliability, full duplex communication, and hot swappable capabilities, which are essential for enterprise uptime. Some enterprise NAS units also include NVMe drives acting as a read-write cache, dramatically improving performance for frequently accessed data. Finally, the network interface cards connect the NAS to the corporate network or SAN fabric. High-speed links, often 10, 25, or 40 gigabit Ethernet, allow multiple servers to access the storage simultaneously with minimal latency. Also observe how this NAS unit has redundant power supplies to ensure continuous operations. In short, while the drives hold the data, it's the CPU, RAM, controllers, and network interfaces on the circuit board that give an enterprise NAS its intelligence, speed, and reliability, turning hundreds of terabytes of spinning disks into a high-performance, fault-tolerant storage system. Next, let's dive into the world of storage area networks. SAN is a high-performance data storage system that typically uses fiber channel or other high-speed network connections to link storage devices to multiple servers. One of the key differences between SAN and NAS is how they store data. SAN provides block-level storage, which allows servers to read and write raw data blocks directly, while NAS operates at the file level, serving files over a standard network file protocol. This makes SANs ideal for high-performance applications, such as databases, virtualization, and enterprise workloads that need low-latency, high-throughput access to storage. Next, let's take a look at the main circuit board at the heart of the SAN unit. One key component of this board is the fiber channel controllers or host bus adapters, HBAs. These specialized chips manage high-speed communication between the SAN and multiple servers, delivering low-latency, high-throughput data transfer. Next, the board includes dedicated application-specific integrated circuits or in some systems SoCs that implement SAN protocols directly in hardware. They handle complex storage tasks like RAID calculations, block-level data management, and error checking, offloading work from the CPU for maximum efficiency. Speaking of CPUs, enterprise SANs often include server-grade processors, paired with ECC RAM that acts as a high-speed cache. This ensures fast, reliable reads and writes, even under heavy workloads. The board also connects to the SAN drives through a backplane or SAS expander interface, allowing tens or even hundreds of drives to operate together, with support for hot swapping and multipath redundancy. Observe that at the storage media level, both SAN and NAS use the same drives. What distinguishes the two is what lies above those storage media. Finally, multiple fiber channel or high-speed Ethernet ports link the SAN to the enterprise servers. Redundant controllers and network interfaces guarantee continuous uptime, even if a component fails. In short, while the drives hold the data, it's the fiber channel controllers, ASICs, CPU, memory, and network interfaces on this circuit board that give the SAN its intelligence, delivering high-speed, block-level storage that enterprise applications rely on. Now that we've explored each system in detail, let's bring it all together and compare how DAS, NAS, and SAN handle data. Starting with DAS, or Direct Attached Storage, the drives are physically connected to the computer's motherboard. The data path is short and direct, giving excellent speed and low latency. Next, we have NAS, or Network Attached Storage. Here, the storage lives on the network, connected through a switch or router, and communicates over file-sharing protocols such as SMB or NFS. NAS operates at the file level, meaning the client or user only requests and writes entire files. The NAS unit itself manages the block-level operations behind the scenes, handling how those files are actually stored on its internal drives. This design makes NAS ideal for shared access. Multiple computers can open and save files simultaneously, though performance depends on the network speed. And finally, SAN, or Storage Area Network. Unlike NAS, SAN operates at the block level. Each connected client sees the remote storage as if it were a local disk. The client can format, partition, and run databases or virtual machines directly on it, just like it would with an internal drive. SANs typically use fiber channel networks, but modern systems also support ISCSI and even NVMe over fabrics, technologies that carry block data over Ethernet or other high-speed links. These allow servers to access remote NVMe drives across the network with nearly the same latency and performance as local storage. So, in summary, file-level access, like NAS, means the client requests entire files, while the NAS manages the blocks internally. Block-level access, like ISCSI or NVMe over fabrics, gives the client full control over how data is organized on the disk, offering much higher flexibility and performance. Together, these systems form the foundation of modern data storage, from personal computers to enterprise clusters to cloud-scale infrastructures. And that brings us to the end of this presentation. Don't forget to check the video description and the pinned comment for a few additional technical details. As always, if you enjoyed this video or found the content useful, please remember to like, subscribe, and share your thoughts in the comments below. Thanks for watching, and see you in the next video.